We put it on the hall.
Hey, for those students who haven't taken a class for me, and I know there are a good group of them in here who haven't taken a class for me, I want to go over how I would prepare for my own exams and what information you have available. What we're going to be doing about that, just before we dive back into content. So yes, this is up on Canvas, it's up in modules for you to take a look at, but I expect people to bring an 8.5 by 11 sheet double-sided of notes to the exam. You can have whatever you want on it. I am not going to be collecting that afterwards for any information or to see if there's anything that shouldn't be on there. I don't care what you put on there. I don't care if you work together to create it and share the document amongst yourselves and have copies of it amongst yourselves. I really don't care. I just want it to be so that you don't have to memorize useless garbage. That is the purpose of the sheet of notes. Anything that you would have to memorize, throw it on the sheet.
Very good at that, all about it.
Yeah. So this material that we've covered, the way that I create these is I go over my own slides and I go through a very large scale, what could I imagine, what exam questions could I imagine making from this material? And I start writing a bunch of questions, and it usually is just a list of a vomited list of questions that I could imagine asking. And there's no way I could reasonably ask anywhere near all of these on an exam, but they're at the kind of level that I would imagine making a question from. So that becomes something that you can use as you're creating your sheet of notes. Go through, even treat this document or a copy of this document like you are writing down the best of your knowledge. What's there? Well, how would you answer that kind of question? And that'll give you a sense of what do you know well, what don't you know well, what do you have questions on? And we will spend some time on Tuesday of next week going over what questions people have. And I'll just kind of dedicate an amount of time until people are happy with, we've kind of run out of questions that are relevant to the material that's here.
And then we're doing this on Thursday.
The exam is a week from today, yeah.
Okay.
So Tuesday will be kind of the review time to ask questions. I want to give you some time between now and Tuesday to study this, write up the best of your knowledge on it, come prepared with, I did my best, here are the questions that I have. How would you answer these kinds of questions? Or what do you mean by this? Or, yeah.
So, how long are you designing this exam to be? Like, are we taking an exam for 2.5 hours?
No, I'm gonna cap it at an hour. And I'm gonna design it to be about an hour in length. And we voted on the first week that it makes more sense from students' perspective to start the class with the exam and after an hour transition back to new content rather than having new content and then ending it with an exam.
I think you're just gonna want to let us go because you're gonna see how defeated everybody is. You're like, these people don't want to learn. These people want to go home and cry.
Yeah.
In addition to that, when I see like be able to walk through a simple application of A star to a small crowd, like I assume that we have a picture we walk through how it works, but then
Yeah.
Is there like, are we expected to write pseudocode or code for any of this, or is it like, okay, it's just like.
Yeah, a lot of this is going to be how things work. If there's a code outcome to anything, I throw that in projects, in applications, something where you have enough time to do that justice and to explore. This is going to be very topic heavy, analysis heavy. Do you understand how something works, when to use something, when not to use something, the benefits and detriments of identifying when to use this versus that, those kinds of considerations. Because I can't easily test that in a project environment. I can see what you submit and I can have you write up something analytical about that process. But I think in terms of the more difficult, I can't assign a project on everything that we go over. So if we're talking about something in a level of depth that I can't reasonably assign or it's too much, this becomes the way for me to target it, get a sense of, do you understand this idea, yes or no? Or to what extent?
Big question.
I don't know, I'm ready yet. For classes that I've taught before, usually I have a sense of what's worked and what hasn't, or what changes I want to make to a past exam in order to make it better, fairer, just different.
That's how I get on Tuesday.
I'll probably have the same answer for you that I haven't written it yet.
Well, we just did 3 questions and we talked about them as a group. Super in-depth conversation for an hour.
Sometimes I do that.
Awesome.
Sometimes I do go back and write questions based on the good conversations that we have on something, so that I know that we've at least discussed this idea before, and I try to change up what's on the exam based on what I know we've discussed. And if you were engaged in that discussion, then you would be able to answer that question and pair that with some things that we didn't discuss in quite as much detail, but it helps me to write it if I get a sense of what people know, and I tend to put that off a little bit just so that I gather more information, more data about where people are. The more data I have, the more fair exam I can write.
So David, what you missed is we're screwed. But you already knew that.
Thomas already knew that, going, regardless of what the content of the class was, that would be Thomas's view of.
Pretty much.
He does,
So.
Yeah, so just a long list of topics and ideas that we've covered, some different general differences between the concepts of uninformed, informed, and local search. When would we use each of them? Yeah,
So. What I'm getting from this is that we should rely mostly on your lectures for saying or.
yes, yeah, this is going to be a lot of what we've talked about in class.
Rather than from the book, that's also part of this.
Yes, if something was important from the book, I would have tried to incorporate it into the lectures, and the stuff that's in the book that's not in these lectures is usually outside of the scope at a level of depth that I don't feel like we can go into within the scope of this course. So yeah, I don't like writing questions unless I guarantee that everyone has had exactly the same experience with it. You've all been in class or had access to recordings. I said that the book was optional. It'd be really mean of me to write exam questions out of a book that I said was optional, that I didn't cover in class. I don't want to be, I want to challenge you, but I don't want to be that level of unfair. That's ridiculous.
I like watching a YouTube video on like iterative deepening of BFS or BFS culture translate all the way you said in class or what would be, okay.
It
Should I
should,
take classes where like this is how we do it, how they do it, like, well, that sucks.
if there's any way to do it, that is something that I will analyze when I grade the exams.
Okay. Sometimes I watch YouTube videos, so.
Yeah, as long as your understanding of that is correct. Sometimes I will have someone say, I watched a video on this and it's like this, and you explained it like this, and your interpretation of the video was wrong, or the video itself was outright wrong.
Yeah.
So use common sense as you're looking at those materials to try to bridge the gap if there is a difference. Why is that difference there? But yes, as long as you can explain it in some way that is correct. I don't care if it's exactly how we described it in class.
I just be from here. I mean,
So yeah, a lot of these are heavy on more abstract topics like examples of things. I do like to write vaguer questions like that that have you generate part of the answer. So I could say something like, what is an example of uninformed search applied to a cyber domain? And your answer to that, there's no one right answer to that, but I will be looking at your answer to say, one is what you put on the page, an uninformed search algorithm, and two, is it the right application for that uninformed search algorithm? Is there a better thing that you should be doing instead? Or is that the right solution to that problem, or a good solution to that problem? If so, great, I don't care what the problem is. It's just, do you understand how to use this tool in your tool belt that we've talked about? And you see the kinds of questions, I try to word my study guides like I word my exam questions where I can. So why would we use iterative deepening over breadth first or depth first search? Understanding of, can you generate either an example or be able to talk about in general why this idea is used over this. So stuff like that, and this just ended up being a very long document because we've covered quite a bit in here already. So everything from global search, everything from local search. Everything from adversarial search. And some material we've covered from constraint solving and some material that we're covering at the end of today. But we're kind of cutting off, by the end of today, we should be at the point where any new material past the end of this lecture that we're on right now is the end of content for the exam. So we should be able to get through all of that today. Are there generic questions at this point that I can answer about preparing for this? We'll have a chance to dive more in depth to exactly what is meant or how I would answer particular kinds of questions next time. But I want people to have the tools to be able to go get started studying and brushing up on material if you're not doing that the last couple days. Anything else? All right. So last time we were here, we were talking about constraint problems. We had the 2 + 2 = 4 problem with letters and a constraint graph, and coming up with, we discovered were multiple solutions to that problem, which was quite cool. We then dived into a little bit of analysis of how do we start to propagate constraints? How do we represent the variables in a constraint graph? How could we use this idea of node consistency to eliminate some of the variables domains? Because when we make a decision, now suddenly it's not possible for that to be something else. So as an example, we started with South Australia, starting with the domain of all 3 possible colors. And then we talked about node consistency, being able to, once a decision is made, eliminate the others. And then we talked about converting constraints into binary constraints, using an example of B is between A and C, or I guess we used one of them based on that. And then here's the other example of A is less than B is less than C is less than D. We can convert that into a set of binary constraints. A is less than B, A is less than C, A is less than D, B is less than C, B is less than D, and C is less than D. So they become binary tests rather than one large quernary test. And then we talked about how to take an all-diff constraint like we have in Sudoku and turn that into a series of binary tests. And it doesn't really matter how large those constraints, that constraint space is. You can always convert it down into some sequence of binary tests. Just sometimes that is very large. Were there any questions on that idea before we talk about arc consistency and how we apply this to more than just the node itself, but to neighboring nodes? Start propagating those constraints and decisions that we make, identifying possible assignments that violate the constraints. We all look thrilled to be here. All right, arc consistency. This is the probably most important algorithm in constraint solving. It's what allows us to go from node consistency, which by itself is kind of useless, to being able to propagate decisions that we make throughout and significantly reduce the space that we search for results. So you can start with a definition. Variable in a constraint problem is arc consistent if every variable in its domain satisfies that variable's binary constraints. And remember that if we have a more complicated constraint, we turn it into a set of binary constraints that are on that node. So phrased another way, we have 2 variables, x sub I and x sub j. They're arc consistent if for every possible value in the domain of the first one, there is a value in the second one, such that we can satisfy the constraints on that edge. So think of them as if-then constraints. If the first one has this value, then there exists some legal value for the second one. if the first value is this other value, then there exists a second, a possible assignment of the second. So for every possible value that we could assign to the first node, there exists some value for the second node that adheres to the constraints. And then we can call the entire graph arc consistent if every variable is arc consistent with every other variable, at least that has an edge connecting it within that constraint graph. As an example, we could put a constraint on two variables x and y, such that y equals x squared. So now we've reduced the space such that for every possible value of x, there's an associated value of y. So for every possible value y, there's an associated value of x. Note that if y's domain had been from 1 to 10 or 0 to 10 before that, we would have eliminated some of those possibilities based on this constraint. If y has to be equal to x squared, then there are some values for y that are not the square of some legal x, which allows us to eliminate them from possible assignments. So making x arc consistent with y, no members of x that don't have an associated element of y such that the constraint is satisfied, and vice versa. To make y arc consistent with x, there cannot be any members of y that don't have an associated element of x such that y equals x squared. So this helps us to reduce that search space. We don't now have to consider a potential value for y that is 8. We don't even have to go down that part of the tree, that subtree. There is no possible way to make the entire assignment for all of the variables on the graph because there's no such solution, but we can figure that out without further exploration than just querying, are these two variables consistent with each other? Questions on the concept of arc consistency? A bit more detail.
Get that last slide for
Yeah, sorry.
You're good.
Thank you for advocating. I do appreciate that. If people are taking notes on something and I'm going too fast, I tend to do that. Please call me out on it. I've also uploaded all of the slide decks that are on the associated first exam study guide. So before there was only the first one. I took a pass over it, realized there's a bunch of stuff we've done, but the material for it is done. So now it is all up. Yeah.
So you're recording.
Yes.
Okay, I'm good.
All right. So our consistency still has limitations. And that involves whenever there is some other variable for which there's kind of a middle ground, there's a constraint that these connections don't specify if we don't look at how they're connected past just those pairs. So we only do that trimming in looking at pairs of variables. Sometimes there are triples, or I'll give you an example of this. So in Australia, there's a particular constraint that South Australia can't be equal to West Australia. And of course, that can be expressed as a set of binary constraints. These are the only possible legal combinations of two colors that could color South Australia and West Australia. Do we trim from this based on, so whatever is chosen for South Australia, we know there's a legal assignment for West Australia, yes. Variables are already arc consistent, is what that means. For every possible value that we could apply to South Australia, there's a value for West Australia that meets the constraint. For every possible value for West Australia, there's an associated value for South Australia that adheres to the constraints. But I guess I'll give you I think that's a little bit, I'm getting ahead of myself ever so slightly. So algorithm AC3 is what goes through and applies arc consistency. So we also do see that these arcs are directed edges, not undirected edges. We have to do these in both directions. And the results of applying it is that if each domain only has a single value, we've found the single solution to the problem. By the time our consistency is done, if every variable's domain has a single value, there's only one legal assignment for each one of those variables. And by making all of those assignments, we've solved the problem. That's only true if there is one solution to the problem. If there are multiple solutions to the problem, our consistency will never get you there. And our consistency won't get you there in a lot of cases. So often there is further work that needs to be done once our consistency finishes, due to the issues with our consistency that we're about to talk about. At any point throughout this process, if any variables space domain is reduced to 0 possible values, it's impossible. No such solution exists to the problem, and you can stop at that point. Stop trying to find a solution, none exists. General efficiency, we have CD cubed. C is the total arcs, so the number of edges on the graph times 2 because of each direction of those edges. And we have the maximum domain size as an upper bound for the complexity of the algorithm, because in the worst case, every single node has that exact same domain size. So it creates a nice upper bound. Maybe a bit less than that. But we're gonna start talking about path consistency, because here is where our consistency really starts letting us down, is for the constraints that have a middleman or a middle node. So the question that is posed, to which the answer is certainly not, is our consistency enough by itself to solve a CSP? For very, very, very small sets of CSPs, yes. But for remotely complicated problems, even something like Australia, coloring Australia, our consistency isn't going to be enough. So you can imagine trying to color Australia with 2 colors rather than 3 colors. So we know it's not possible, but if we applied our consistency to that problem, it wouldn't reduce the domain at all. Can anyone explain or have some insights into why it wouldn't reduce that domain at all?
Yeah, not just because there's still only like in your example, it's like red, green, red, blue, that. Like,
Yeah.
I can't think how to put it into words. There's still there. Yeah, I don't know how to say it.
Is it the limitation of you only have such a small amount?
We're comparing everything to its possible neighbors, but without the scope of looking at the entire problem. So imagine taking a very first step in Australia and picking, all right, I'm going to choose this area and I'm going to make a choice for its color. Is there a possibility for each pair independently of each other? And the answer is always yes. So if we go back to and analyze, we'll actually look at the picture of Australia to get a sense of this. We only ever look at pairs of these. So someone give me one of these locations.
Northern Territory.
Northern Territory. So we're going to start here and we make some kind of decision on that it's going to be some color, like blue. Now we can start to look at edges of, if this is blue, is there a legal coloring for Western Australia within the constraints?
Yeah.
Yes, the other 2 colors. Is there a legal, just looking at Northern Territory and South Australia, is there a legal coloring between them? Yes, the other two colors.
Are we, is this example that we're doing right now, like off of the presumption there are only two colors currently instead of the three that we were already?
Yeah, so if it is two colors, red and blue, then we would look and we would say, red is possible.
Yeah, okay.
Red is possible. Red is possible for every neighbor for this. So two colors doesn't reduce the domain at all. We can't say Northern Territory can't be this color because of that reason. Yeah,
So it wouldn't reduce it because it's always, like, the edges are always valid, right? Cause there will always be a valid color if it's one other color, but like, if
it
you had.
involves a third variable in order
Yeah.
to make that.
So if there was
connection.
only one color, would it reduce it then? Because
Yes.
it wouldn't be.
One color is
valid.
possible. Yes.
Okay.
Yeah, exactly. So if there is one color, then we would say, if we select a value for Northern Territory, is there a legal value for South Australia? No, the one color that if blue is the only color we're using, for every element that this could be blue, is there a legal value that this could be such that the constraint is that they're not the same color? No, there is no selection of only blue as a possibility. The only possibility would be blue, in which case the neighbor is blue. So that's a problem.
So if we introduce the three colors back into it, they would still not reduce it, right? Okay.
Yes, yeah, but it even doesn't reduce it in two colors. I think that makes it easier to see.
Yeah, it does.
Because to the critical thinking mind, obviously two colors is impossible. But applying just this algorithmic idea, the idea of you needing a third territory, and an edge only connects two vertices. So you need a third territory of assignment in order to understand that there is a problem with the two color. Let me actually draw that out. So if we make an assignment here, and we make an assignment here, now there is something that says South Australia cannot be something that doesn't violate this constraint or this constraint. But we have to be considering three nodes when we do that, and arc consistency only ever looks at two nodes. And every pair that you could possibly think of in this entire, there's never going to be a constraint violation, just looking at pairs of vertices.
So I'm just having like kind of issues picturing like where arc consistency would be useful.
Yeah, if it doesn't do that, yeah,
Yeah, if it's only comparing, I mean, I guess like if you have like a minimal problem where you're looking at two nodes, but.
yeah, sometimes it can reduce the domain. The goal is not to solve the problem usually with arc consistency, it's to reduce the search space. So that when you do make a decision about, well, which of these are we gonna start with a possible assignment, instead of having to look over every possible value for this, if you've been able to trim that search space, then you can significantly reduce the complexity of the problem through the reducing of that search space.
Okay,
But
that
yet,
makes sense.
very rarely is it going to solve the problem for you. Only if a human could have easily seen the problem, the solution to the problem outright, is arc consistency alone going to solve the problem. It is a search space minimization tool.
Well, once you have this constraint met from the first node, when you start off, don't you just assumption to jump to the next node, check every other?
We're actually going to talk about that. But yeah, in general, we're going to use some kind of depth first search like algorithm where you're going to choose somewhere, make a decision on it, and then search the subtrees for that. But the subtrees are going to have a smaller branching factor if we've eliminated via arc consistency possible branches from that assignment. So it's a pre-processing step to save you lots of repeated work later. This class has a lot of optimization, a lot of discussion on optimization. When do you pre-process? How do you pre-process to make a large scale task more efficient? And again, I see that as being hyper related to every cyber implementation that is out there. It's just being able to know when to optimize and to what extent you can optimize. Back to the slide we were on, which is here. So yes, reduces the domains of unary constraints by analyzing the binary constraints. I think it's a great way to summarize exactly what arc consistency does. For any unary constraint, something that only affects one variable, we're going to look at the binary constraints and say, can we get rid of something like, we know that this territory cannot be this color by looking at the associated binary constraints. But In a 3-color problem, there are ternary constraints. And the ternary constraints are what make the problem more interesting. So path consistency is going to allow us to reduce the domain of binary constraints by using constraints inferred by looking at those ternary constraints, or implicit triples of variables. So now when we look at, if we color one color and a neighbor is this color, is there a legal value for the next? So that is path consistency. You would think that, well, if we have path consistency, what is the point of arc consistency? It seems like it's outdated at this point. We should just apply path consistency. The issue is that path consistency is intractable in most cases. So for every single 2-variable set, we have to make it path consistent with every other neighbor to that connection. So now we're looking at edges of size 2, with 2 edges that connect 3 vertices. And we're trying to figure out, is that third vertex consistent with the binary constraints from setting values of those 2 variables to be some. So it's just applying that to one more dimension, one more variable. For every possible pair of assignments between those 2, is there an existing value of the third that is legal? So you can also think of it as a path from start to end, going through a middle state. Is there a legal value for the middle state given the values of the start and end? So this is the process that breaks the 2-color problem and shows that it's impossible. Our consistency didn't reduce that at all, but using path consistency, we can show that the problem is impossible. So when you try to make Western Australia and South Australia consistent with, I already forget what NME stands for.
Northern Territory.
Northern Territories. When we try to do that, we find that no pair of assignments for Western Australia and Southern Australia allows for us to color Northern Territory in any way. But because we iterated every possible coloring for those 2, of which there's really only 2 in a 2-color environment, either one is red, one is blue, or one is blue and one is red. And either way, there is no way to color Northern Territory red or blue, because one of them adjacent territories is that color. But it takes path consistency to see that. So our consistency gives us 2 valid assignments, and each of those options, the size of the domain that is consistent for Northern Territory is 7. So because of that, we can abort, reject. There is no solution to this problem, the 2-color problem. Questions on path consistency? But why stop there?
Hopefully, there's more.
Exactly. So of course, we could propagate constraints to more than 3 variables. We could look at 4 variables, or 5 variables, or 6 variables, and the associated binary constraints between all of those sets of variables. But you see how the size of the problem is starting to grow exponentially. For just path consistency with 3 variables, you have to think of every pair and every possible neighbor of every possible pair for every possible pair of assignments for that pair. If you're going to look at 4 variables at a time, we need to look at every possible neighboring triple, assign every possible combination of assignments within that triple, and ask for every neighbor, is there a valid member of its domain that can be assigned? And that just that's an exponential size problem. It gets harder and harder to be able to go through everything to find those constraint violations. So definition, we can call a constraint problem k consistent if for any k minus 1 set of variables, there's a consistent assignment of those variables, we can always assign something to that kth value. So it's 4 consistent if we look at every triple, and for every neighbor of that triple, there is a legal assignment for that triple. for some combination of values of assignments of those three variables in that triple. And then we can make 5 consistency and 6 consistency and 7 consistency. It's just that at this point, we stop caring for the most part because even a small problem becomes intractable at 5 consistency, 6 consistency, 7 consistency. So node consistency by definition is 1 consistency. And arc consistency is by definition 2 consistency. And then as long as we have a binary constraint graph, 3 consistency is identical to path consistency. And that's only if all of your constraints are represented as binary constraints. Last definition you might care about, we can say it's strongly k consistent if it is k consistent and k minus 1 consistent and k minus 2 consistent all the way down to 1 consistent. That means that applying node consistency, arc consistency, path consistency, all the way up to k consistency for some k, none of that can remove anything from any domain. There's always a legal way to solve the problem. There's no information that we can get from that allows us to, within a particular assignment or assignment pair or assignment triple, find the counter for that. So if we have a graph with n nodes and make it strongly n consistent, we can solve it immediately, really easily. You just choose an arbitrary value for the first one, the first node. And we know that since it's 2 consistent, there will now be a legal consistent value for the second node. And given that it's 3 consistent, there will be a legal value for the third node. And if it's 4 consistent, then there'll be a legal value for the fourth node, etc., until you have a legal variable assignment for the entire graph. You just basically get to choose from the domain some legal value. So having something that is strongly n consistent is a phenomenal way to, it's great. It's just that showing that is a very difficult problem.
Yeah, I got a question.
Yeah.
I'm not sure if I'm gonna be able to explain this. Yeah. Ask this. Shut up. Agree. So if we have something that's more than, like we have something like a ternary thing, there, like the highest consistency we can go is 3, but we can make it 2 consistent. We would just like pick 2 of the 3 constraints. Kind of.
I don't think quite right. So we can make Australia up to 5 consistent for a 3-color problem. It just says that for every 4 decisions that you make that are consistent with each other, there exists a 5th node, a color that you can assign the 5th territory that is consistent with that.
I think I was thinking of between nodes, so. Never mind.
Yeah, and even though some of those will be the same color or the same value, but it's just saying for every group of 4 adjacent territories, you can assign the 5th one a value. So total runtime of that n squared times d. Of course, constraint satisfaction like this, NP complete in general. So trying to apply this in general to a generic problem is going to have exponential complexity. So in general, anything that's trying to establish inconsistency is going to be exponential in both time and space with respect to the size of the problem, which is of course intractable as that scales past about 10. So this is a way to identify a solution to a problem. It exists. It's just takes a painful amount of time and space to calculate. We'll talk about some ideas of what we could do about that. But let's talk about handling global constraints in a minute. So this is like the all diff constraint in Sudoku, something that tells us that every value needs to be different, or the sum of all values assigned is at most this, or something like that. So there are special purpose algorithms if you can create a problem or phrase your problem in terms of global constraints instead of sets of binary constraints. So sometimes, instead of just having those binary constraints, analyze the problem, come up with an associated logically equivalent global constraint, and then you can apply a more efficient algorithm to it. So constraints like all diff. So let's take a look at this algorithm and analyze it. Remove any variable in the domain with a single possible value. Delete that value from the domains of every other variable in each all diff constraint that this variable was a part of. This is a common Sudoku. I don't want to say strategy, but it happens in any Sudoku solver. You place a 9 in an associated row, and it removes the 9 from every other possible cell in that row, and every other cell in that column, and every other cell in that cell in that large cell box.
Can't you,
Late for me too.
can't you apply this to blackjack?
Yeah, you can apply it to just about anything. Yeah, so is this doing any kind of arc consistency or path consistency? What is this doing that would save us a ton of time with regards to kind of the brute force algorithms that I just showed you? Yeah,
As you make removals, you're like reducing the domain space overall,
yeah,
so there's just less stuff that you have to worry about.
yeah. It's going through path consistency for if this was a 9 and this was a 9, it's violating that particular constraint. So we just remove it all without having to consider every possible other row or column. It's just everything that we could possibly do with that information. We're just going to remove it from it to begin with. So yeah,
I'm unfamiliar. So the Sudoku, you have to, it's 1 through 9, right?
Yeah.
It has to add up to a certain.
just you have to have a separate digit in each, all of the 1 through 9 digits in every row, column, and 3 by 3 cell.
But they can't be in the same row column. Jason.
Right. So yeah, once you have the 9 identified for a row, no other cell in that row could also have a 9. So using logic, you want to reduce the domain down to this cell has to have this particular digit because every other possible digit violates a constraint. It appears in a row or a column or a box or something more complicated than that. And as we do this, if we create an empty domain on any other cell in the Sudoku, then the problem can't be solved. The Sudoku is unsolvable. If we ever have more variables than possible values, then the problem cannot be solved. If we use this kind of constraint, the 2-color Australia problem is solved very easily. We just put an all diff constraint on 3 neighbors. If they're all neighbors to each other, then phrasing this as an all diff constraint between those 3, now we can identify that there are only 2 colors. These 3 have to be all different. No matter what 2 we assign, if we create that empty domain in one of them, we can't have that assignment. So we very quickly can determine that the entire problem is unsolvable because of an all diff constraint on just 3 territories. So if you can phrase that problem like that, we can find a much more efficient than just applying arc consistency, path consistency, K or N consistency across a much larger problem. So taking an analytical approach, breaking down the problem and saying, are there hidden constraints in this that I can phrase in terms of more complicated constraints that are global constraints on the problem, even if they're locally referential? If you can't solve that subproblem, then it means that you can't solve the larger problem. questions on converting something into a global constraint? Why that might be a useful way to spend your time? Next kind of constraint that might be useful to you is a resource constraint, also called an at-most constraint. As an example, we have 10 personnel and we can't assign more than 10 people in total to 4 tasks that we need to be done. So you would write this constraint as such. At most, we have 10 people to split amongst task 1, task 2, task 3, and task 4. How many ways could we do that meet the associated criteria? Quite a few. But if we allow for other constraints that we write based on this, we can start detecting that there's no reason to continue searching the space. Like, for instance, are there any edits that we can make to 3, 4, 5, 6? Well, 1, it's more than 10, but how could we reduce the domain?
I'm not sure I'm tracking, can you?
Yeah, so like each one of these tasks is gonna start with a possible domain of there can be between 1 and 10 people. And it doesn't make sense. You can quickly eliminate 10 because as soon as you assign 10 to task 1, then there's no one assigned to any of these other tasks. Which I guess by the wording of this problem could technically be a legal assignment. But if we needed at least 1 person assigned to each, or if we needed, we can start to think about if we assign different values to different, what does that create in terms of the associated reduction of domain?
So 3, 4, 5, 6, they were supposed to be 4, 5, 5.
No, it's not. It's looking at those as the domain of what can we say about if T1 is 3, then something else. So we end up being able to determine something like, if we see something like a 3, a 4, a 5, or a 6, then the problem is intractable. If the domain for a particular variable ends up being 2, 3, 4, 5, 6, then we can delete 5 and 6 from that domain. Think of, yeah, so what this is saying, let me actually write this out in a way that makes more sense. I wish I had a little bit more space for this, but the idea is that we have 3, 4, 5, and 6. We reduced the domain down to these values. And they all have to be filled in some capacity. So if that were the case, we don't necessarily have to select all different, but as soon as we select 3, 3, 3, and 3, we're over the 10, which is kind of a minimum value that you can pick from here. So we can quickly identify that there's no legal assignment of these variables because we've eliminated everything else already. So we find ourselves in this subproblem. It's a really easy subproblem to solve.
So is the idea that you would check like the minimums to make sure it falls within the constraints of your resource itself?
Yeah,
Okay,
yeah,
so the domain is just the choices that you have. for
Yes.
the- Okay,
yes.
that's what I was missing, cause I felt that
It wasn't clear until I
first
said
bullet,
that,
when the
yeah.
first bullet point came up, I thought 3 was like task 1, 4 was task 2.
Yeah, no.
Not the domain to the choices of the
Yeah,
task.
I got that hint from hearing what you all were saying. Like, I gotta clarify that the possible domain is for each variable now. We've eliminated everything else. This is a subproblem of this problem. If we find ourselves in this subproblem, there is no possible assignment
Yeah, okay.
of these values to these that meet the associated global constraint. Or I guess resource constraint. With
So the-
1, 2, 3.
The 3, 4, 5, 6 is just. I mean, it just says it's the domain, but that represents how many people we can assign to that task.
Right.
Got it.
So somehow we've eliminated 0, 1, and 2 as well as possibilities. So we have to assign, and we can assign the same number of people to different tasks. But by looking at the minimums, we see that that violates the resource constraint, and that since every other value is larger than that, there's no possible assignment. We don't have to go through, if we assign 3, 3, 3, 3, 3, 3, 3, 4, 3, 3, 3, 5, 3, 3, 3, 6, 3, 3, 4, 3, etc. We don't have to iterate through all of those possibilities. We just check the minimum, see the minimums of each is intractable based on an at most constraint. As soon as you see at most, minimums can't go, can't create a solution to the problem, the entire problem's intractable, has no solution.
So for that same reasoning, that's why 5 and 6 can go on the second one, because if you choose 5 for any of them, there's no possible solution.
Right. Yep.
Okay.
And so for this, now the domain is 2, 3, 4, 5, 6. And if that's the case, yeah, as soon as we have 5 somewhere, we have to split, even if 2 is chosen for everything else, 5 plus 2 plus 2 plus 2
Still over.
is over 10.
Yeah.
So we can eliminate 5 and 6 from all of those domains, because as soon as one of them picks 5 or 6, the rest of the problem is garbage. So this domain can get rid of the 5 and the 6 and should immediately be reduced to 2, 3, 4 because of the at most constraint.
This particular constraint feels a lot like linear programming.
It is, yeah. Other questions on this, or what this is representing, or what the associated result of this is, just through analysis of a constraint? Like, our consistency wouldn't get this, because we'd be looking at pairs of tasks and assignments of pairs of tasks. We would find that everything is basically consistent. If we assign task 1 6, then there exists a task for task 2, like 2, that meets the at most constraint. 6 plus 2 is 8, we're under the 10, we're good. Because we're only looking at pairs of things. We wouldn't be able to eliminate or reduce any of the domain.
This might be a trivial question, but in the first domain, 3, 4, 5, 6, anything doesn't work because we look at the minimum and we don't have enough people to even satisfy
Yeah.
the minimum one. In the second one, we introduce the 2, which then makes 3 and 4 valid solutions, where in the first domain, they're not valid.
Correct.
Do we have to just check? I guess there might be a smarter way to do it, but we kind of have to check all of the values, right, when we go to.
You kind of, if you make an associated assignment of 6, you can now start with the largest possible and say, is there a remaining assignment that works? Start with 5, is there a remaining assignment that works?
We could do like a. Not estimated, like an educated brute force almost.
Kinda, you
Okay.
could start at the top and say, is
Yeah.
there a legal assignment? But yeah, this helps us to be able to use some kind of constraint like this in a way that the consistencies that we've talked about would struggle.
So this is path consistent as well, right? Because that
Yeah.
requires 3, so because 6, 2, 2 works, but that doesn't reduce your domain, so.
Right, yeah, so path consistency wouldn't even find this, and path consistency is pretty expensive, we'd be looking at every triple assignment.
For
1, 2, 3, 1, 2, 4.
Yeah.
And that would be, this is way less work than either of those. So how you state your constraints matters. Lost. Further questions on this? I recognize that this didn't make sense at first, but hopefully it does now. Talked about it long enough that it makes sense again. Good.
Again, it's a funny word that.
Right. All right, so if you have a large resource limited problem like this, it may not be easy to represent as just a list of integers, set of integers. So something like we have 1,000 people and we have, I don't know, 400 cars. What assignment should we use? Is there a valid assignment? Maybe 400 is too much. 300 cars, 250 cars. Is there a valid assignment of people to cars that transports everyone from location A to location B? And now, even with at most constraints, it's going to be very difficult to reduce that domain. That's a tough problem even to use this on. So you will use something like bounds propagation, which is what we're going to talk about next, to solve those kinds of problems where this starts to scale. So bounds propagation. Yeah.
Before I keep going.
Sorry, oh, break. Yeah, I guess we can. Yeah, we'll take a quick break. Try not to take 10 minutes this time, just because we want to cover a good amount. I don't want to cover new stuff for the exam on Tuesday, so I want to get through a good chunk, but a good 5 minutes for sure.
What's up, bro?
You guys chart. All right. Oh, yeah. I have the world's easiest problem for you now.
Is this the world's easiest risk problem or like an actual risk?
It's pretty close to equivalent.
Because the means not true for my brother.
Yeah, no, this is way easier.
I thought this was fun. All right, Chris, what was the best way to implement stories? Was it just a divided subgraphs or not even process for JSON, just converse the JSON?
I would estimate the size and I would come up with a number of landmarks and I would try to equally space those in some real time.
That's what I trained.
I tried and my computer is bound by it. I don't know how.
I tried and it took over 5 minutes, a very large graph, like 400,000 nodes.
Yeah.
What's the actual list size?
So you would figure it's gonna take about this long to parse through that, so I need to select some number of landmarks randomly, depending on how much time do I have the ability to create equidistance between them. And calculate that, the answer is probably no, so you sort of estimate, guess.
Next time when we get the later expecting, my original solution worked on, you tested. And I was testing on like sizes of like 5 million nodes, like 10,000 vertices, and it was breaking there, so I was like, cause like we were going to the extreme, me and David were probably ducking off each other.
You said we were gonna get JSON files that were already big, and I couldn't generate anything close to that.
I had to modify the original, I probably should have done this originally, but I had to modify the original graph generator to do dense ones faster when I wanted to make a really dense matrix. And then I think all the ones I tested were
Well, I just went through.
100 megabytes or like 700 megabytes or like 1 gigabyte.
Oh, yours is gonna be way bigger than the one like this.
Yeah, it was just the really dense one that was a gigabyte.
Oh, got it, okay.
So
That's
I'd rather,
not
not like blaming anybody, just can we get the input next time? I
Yeah.
wanted to
If
bring-
we,
Yeah.
I can post it online as well.
so my program would crash. If the program didn't crash when it ran out of memory, but it still found a solution, would that get more points than if the program crashed? So like,
Yes, that's a better,
I would run out of memory in a gigabyte and it would just stop because I ran out of memory in a gigabyte. If I just let it, like, if it didn't crash, I let it use all the memory in the world that it wanted, and I found a solution, would that give more points than if it crashed early?
I don't think so, because in a containerized environment with a gig, they're equivalent to each other.
I don't know, just when I seen in the test results, I was like, you were closest window, but I was on the first, so it was okay.
Fair.
I was just. At least the programs that I was testing. Even with small files using the original one, or like moderately smaller files, they blew way past the 1 gig limit. So I have no idea how the average was
Weird.
that high, because I know that a lot of the programs shit themselves on at least the memory problem, on the memory constraint, and then the 60-second constraint, like some of them will just go on forever.
Yeah, there has to be some kind of intelligent choice made about how to approach the problem based on the size of the graph. Or an estimate of the size of the graph.
I guess that the technical solution to it wasn't necessarily the problem I'm having with that, but
The way it was graded or like.
I just don't know how functional these programs are.
Only one of them did perfectly, and even that one, I think, about 68 seconds on one of the graphs. It wasn't, however.
I have a follow-up question.
Yeah.
How did mine fail a dense graph, but did fine on the denser graph? Like 100 edges per one node doesn't work, but 1,000 edges per node, it cooks.
It could have just been
That's bizarre.
the actual structure of the underlying graph.
Huh.
I can imagine that there are certain setups for graphs that it just does not handle particularly well, or there's some bug in it that doesn't handle that particular setup that may be independent of the size of the graph, and if the dense graph and the denser graph align to the dense graph gets the bug, and the denser graph does not, based on how it was generated, then it's likely not the size of the graph being the reason for that. Something else happened.
Yeah.
Anyway, this really easy problem's been up for a while. Has anyone solved it?
Is it 165 and 385, or is it one?
Yeah, we can fill them with anything between the minimum that they can fly with and the maximum they can fly with. Crazy. We did it. However, you don't want to list them out as sets, so you just list them as a range. Now, there's an additional constraint. 2 flights will only run if the combined passenger count is at least 420. So how do we reduce the domains?
Just be 420 for both.
Now we're talking about the combination of the total passengers aboard both planes. And you can't shove 420 people onto a single plane. So what are the domains of anything that's outside of this domain? Automatically, there's no solution to the problem. But inside of the domain, there exists a level of fullness in the other plane such that we would fly them both.
If you pick a maximum for one domain, the minimum of the other domain would have to be enough to satisfy the requirement. You do that both
Yes.
ways.
Yep, that's exactly right. So as an example, we pick the 165, how many people would need to fly the other in order to run them both? The answer is 255. You pick the 385, how many need to fly on the 165 in order for that to happen? The answer is 35. Just both the maximum of one and the minimum of the other add up to 220. So this doesn't mean that every possible selection is consistent with the constraint. It doesn't mean that if there are 35 people on plane 1 or flight F1, then we're going to fly. It just means that there exists a value in the other domain that such that we would fly the planes. So anything that is outside those domains, we no longer have to check the other flight. We just cancel them both. So for something to be bounds consistent for every variable and each of the upper and lower bounds of that, for every variable y that depends on it, there exists some value within the bounds that satisfies the constraint between that. So bounds propagation allows us to very quickly eliminate large swaths of a search space when we're dealing with lots of information. This would help us with the cars and people in transporting problem on the last slide. We talked a bit about applying this to Sudoku, but I'm going to give you an example. For those of you who have solved Sudokus before, question I would have for you is about how long would it take you to solve this Sudoku?
Done.
Oh, yeah.
Wanna watch me do it again?
20 minutes. Any guesses, given what you see here at the difficulty of the Sudoku? If it were an easy, medium, hard, if it were some other form of measurement? Regards to pretty difficulty.
This is
Just
a
looking
easy
at it.
Sudoku.
Yeah.
Say.
Because there's a number of them that already have 5.
And 9.
Oh, I just mean 5 total entries.
Uh,
So like the middle top box and the middle bottom box both have 5 entries in them. So those would be easy to fill in, and then you just kind of go from there.
This is pulled from an easy Sudoku database.
Yes.
So by casual Sudoku players, this is probably solvable in 15 to 20 minutes. For someone who solves these for fun, you can probably do it in 5 to 6 minutes, possibly faster than that. Any guesses on the speed of a constraint solver? If you threw just the algorithms that we've talked about so far, an actual constraint solver that has been optimized to solve Sudoku puzzles.
0 seconds.
5 milliseconds.
Yeah, maybe it's better to ask how many puzzles could be solved per second rather than. Do you think that just with constraint propagation, as we've talked about, just using all of this, you could solve a given easy Sudoku?
Like pretty quick.
Could you solve a medium Sudoku?
Maybe. Probably.
Hard Sudoku?
Probably.
How does it get harder? I've never done a Sudoku in my life.
So
Make it
you
more
get
efficient.
less numbers to start with or more boxes. And you can't have them overlap. So the less information you have to work with, the more likely you're to put a number in the wrong spot, which will fuck you up later.
I think of it in terms of a branching factor of given the information that is here, how much information could you reasonably put into this in the moment? How many different numbers could you fill in with the different information that you have? Or numbers could be eliminated from certain cells? If the answer is a lot, given the information that's there, then you have a wide branching factor. Whatever it is that you consider, you'll probably find one of those pieces of information. The hardest possible Sudokus are ones that if you apply all inference to every possibility, there's only one piece of information that you can get. And getting that one piece of information reveals one more related piece of information somewhere else in the puzzle, which reveals one more related piece of information and just kind of does that throughout. It becomes a very linear, you have to see this before you see this, before you see this, before you see this, in order to solve the puzzle. You don't have options.
At one point, if you play on expert, you have to like guess a number and then just go along with that.
Right, you gotta do a depth first search. They do though say that everything can be solved logically. We're just gonna do a deep dive into this idea of how well can constraint solvers solve problems before you need to go into a search. Are all Sudokus that are actually out there and publishable, are they solvable with just logic, or do you need to do a search to be able to solve a particular published Sudoku?
I think like all the ones that they publish, there has to at least be one like choice that is like guaranteed to be like the correct thing. Like the professionally released ones, you're never guessing.
Right.
Like there's always at least one thing you can do, and it might just be like that you follow a linear structure the whole way through, but like you are guaranteed at least a single placement at each turn. Whereas this one, like, there's probably like 5 or 6 right off the bat that you can just like guarantee, like for instance, in the middle center, like you're guaranteed that one goes in the top right corner, so it'd be 6A.
Yeah.
It's the only place they can go, and you could probably do the same thing with the bottom center one as well, like.
Yeah.
You have the 9 as well.
But constraint solvers can solve thousands of puzzles per second, which is pretty impressive given how difficult this is for a human. So we know if we're going to represent this as a constraint problem that we have 81 possible variables, one for each cell that's going to contain one of the 9 digits. What are the constraints? How would you formalize the constraints of a Sudoku?
Row and column.
Rows, columns, and 3 by 3 cells.
Yep.
So, yep, those are all diffs. Do you need any more than that? Are there any additional constraints? If you meet all of those constraints, have you solved the problem? I would answer you have, because the numbers that are placed there initially guarantee that there is a single solution to it. So that given the information that's there, if you're able to meet those 27 all-diff constraints, you found the only one solution that is consistent, unless you're able to erase some of the numbers that are already hard-coded into the solution. So you don't need more than that.
Is this like how they would create them in the first place? I don't
You
know.
kind of backtrack. You
Yeah.
use logic to say, what can I delete? Can I come up with the logic to place that there? Great, and then just continue to backtrack until you run into an associated dead end. If it's a dead end, at that point, you can't remove anything else without being able to put it on. That's more of an expert puzzle. If you just stop earlier than that, if it's a beginner, moderate.
That's just a common question, like, random question again. Do puzzles only have one solution?
Yes. Published ones. Granted, it's possible that you can create, if you just randomly generate and fill in some numbers, then imagine you filled in no numbers. Every Sudoku that's out there is a different solution. So if you don't have any information, then there's a very large branching factor. So the difficulty is in providing just enough information that you've narrowed all of the possible solutions down to one possible solution, given the information.
So what you're saying is the most optimal place to start first transition in this, if we go back to like.
Yeah.
Maybe that could be a row call or information, rather than it aside, so there's it's a own way to solve an almost empty row call.
Yeah, we're gonna start thinking about how would a constraint solver, if you were writing a generic algorithm to solve a generic Sudoku, how would you start to approach that? So first question I would have for you, if we're applying arc consistency, how much information is just arc consistency going to give us? Is it gonna give us nothing, or is it gonna give us something?
Isn't it just like the nearest neighbor, so it wouldn't be helpful at all?
Like if it's looking at two at a time.
The answer is not none.
Okay. Start with the dance area.
So as an example, E6, we remove the domain as soon as we find that it violates a constraint, because as an all diff, we need to make sure that everything is all different. So if we find a particular assignment that violates one of those constraints, then we can remove it from the domain. And as we iterate over everything in the row and column and cell, we eliminate every other possibility that it could be. So column constraints, then 3x3 constraints leaves us with the domain of a single value, which can be locked in. Note that this only works if there is a 1 through 9 minus what it should be somewhere in the row, column, or 3x3. And that is not the only logical way to deduce what goes into a cell. But for any cell that can be filled in using exactly that trick, then our consistency can find it. And what's interesting, for very easy Sudokus like this, our consistency can actually get you the entire way to the solution. Without looking at any, if I do this and this, how do I reduce the domain of this, of incorporating a third variable? The information that you get from applying a 4 to E6 unlocks the next one, unlocks the next one, unlocks the next one, to the point where the entire thing is filled in.
So I just wanna make sure I'm understanding, if you were to give like an expert level one, where like say like each one only has like 2 numbers in each box, right?
Yeah.
Then our consistency won't get you very far because it won't be able to reduce the domain as much because there's less information to pull
Yes.
overall, okay.
Exactly. So beginner Sudokus can sometimes fully be solved with our consistency, but that's about as far as our consistency can take you with regards to. Eventually, you need more complicated, utilizing more than just pairs of variables in order to logically deduce what goes where. So yeah, in general, AC3, the algorithm for our consistency, only works on the very easiest Sudoku puzzles.
One more question,
Yeah,
so like,
that's good.
if you were given an expert on arc consistency on it, it would have to run arc consistency on all of them until it found the one where it would reduce the space.
Well, we'll be able to reduce the space of each domain by, you start with, any cell can have 1 through 9 in it.
Yeah.
And you can only place something that you know for sure if you reduce that domain down to size 1.
Well, I guess that's what I'm thinking of, is like say that there's like, you get an expert level 1, and then there's like one box out of all of those boxes up there where you're guaranteed like arc consistency will reduce the domain to 1. So you have to run through every single box until it finds that one, it would place a number, then you could run it again, you have a little bit more information, and then hope that it could find that one domain again.
Yeah. And as
Okay.
long as you always have a domain of 1 somewhere in the puzzle, there's new information that you can get,
Yeah.
which propagates to the rest of the cells that affects, which may reduce the domain of some other cell to 1, which allows you to use that information, which allows you to, but you see that that's not particularly advanced logic. It's just using the simplest logic available to you. It's not considering anything more advanced than that. So that's why I can only solve the easiest of puzzles, and humans use much more advanced logic to solve the more difficult Sudokus.
That's how my brain works when I do these, so.
People still casually use Sudoku, things.
I don't know my phone, there's a little app.
I remember the my phone was like faster, little, I'm like, okay, it's like a stack. I haven't seen it since then.
For me, it was always logic puzzles. I had books of like the kind of box, you give it a number of clues and you have to determine which clues match to, you want to figure out which person was on which day at which time did something or other, and the logic clues say, you know, this person did this 2 hours later than the person whose dog was, unrelated clues, and as you get more information, those clues start to unlock more and more of the domain of that to be able to determine how every variable is related to every other variable.
Just a game. Just like,
A little bit.
kept saying included, it really is. I was like, it sounds like.
Yeah. So what's interesting about this, I introduced a concept of Sudoku because nothing about the constraints that we placed there had anything to do with the actual Sudoku. That wouldn't apply to something else, like the all diff of 9 things in a row, or just everything in a row is unique, everything in a column is unique, everything in a 3x3 cell is unique. Nothing about that formulation, it's just the all diffs for that is unique to Sudoku. It's just a constraint. So the constraints don't necessarily define the domain as much as we can utilize these concepts of constraints on whatever problems we see in the world. So every strategy and everything that we've talked about with regards to Sudoku can apply to any constraint solving problem. And so many problems can be phrased as constraint problems that we can utilize these techniques all over the place. You don't have to have an understanding of the domain at all. You just have to understand the associated logic to be able to phrase it in terms of a constraint problem. And as soon as you do, you can solve it without having any further knowledge of the domain. You can imagine that you're introducing someone to Sudoku and you just say, the problem is that there are 27 all diff constraints. Solve these all diff constraints. And you don't even phrase them in terms of rows or columns or boxes. It's just, here are vertices, here's the domain. Here are the groups that need to adhere to these all diff constraints. Done. And a constraint solver with having no idea that it's playing Sudoku, what the rules of Sudoku are outside of the constraints themselves, which kind of are the rules, but without for any further logic, it can deduce and solve Sudokus. This is past art consistency, using the rest of this and being able to solve even expert level puzzles. Doesn't need to know any more about it than just the rules phrased as constraints. So we never need additional domain specific knowledge. So it's a very general tool, which is really exciting. We ready for project 2?
Keep that shit away. You just said you need to study for the thing, just we'll worry about project 2 after next Thursday.
Okay. So this one's much easier than project 1. This is the break between the hard projects. This one will be hopefully significantly easier for people. And so I will have you going to this link, and I'll click on it in a second so that we can open it up and take a look at it. But it is Sudoku constraint code written by the author of the AI textbook that I pulled most of this from. So your tasks for looking at this is to implement the constraint code yourself. I don't really care how meaningfully different it is from the code that's there, it's complete. But I want you to have a chance to just kind of plug and play, ask yourself, why does this work? How does this work? Using the linked code as some way of understanding the underlying process of solving a generic Sudoku under the guise of a constraint solving problem. As you do that, just make sure that you're understanding exactly how that solution is put together. Tie it to the content that we've discussed throughout constraint solving. And then just quickly write out, this doesn't have to be long, summarize what you learned and or observed by implementing this code. Why does it work? How does it work? So simple task 1. Task 2 is to research and find improvements to the code. So yes, this was generated by an author of a textbook, but it was also written 4 years ago. Some things have happened in the last 4 years. So you can imagine that this is kind of like a cyber application where you need to take a very constrained portion of code and update it using the most state-of-the-art techniques. So research and look for, have any techniques been found that might make this code more efficient? Be able to solve more problems faster, or be able to solve more complicated problems and not spin its wheels quite as much on the most complicated Sudokus for that. For task 3, you'll just look at the code's readability and maintainability. And I want you to be able to determine how readable was it and think about being able to join and extend this code. It's written fairly professionally, so just getting a sense of what does that look like? How easy is it to engage with? And then finally, just identifying cyber applications that can be modeled as a constraint problem. So trying to come up with how would you model this problem as a constraint problem? How would you set it up to have a constraint solver help you in some way, shape, or form? So you would discuss the problem, how you would formulate it as a constraint solver, how would a written constraint solver solve the problem, and any potential weaknesses of using a constraint solver to solve the problem. Would that lead to any vulnerabilities? How would you attack that? What are the associated time and space constraints? Is that going to be feasible given the size of the application that you need when you're applying this to whatever cyber application you picked? What concerns would you have about using this approach? So my thoughts on this, about 2 pages of single-spaced report for the entire thing, plus the code that you write for it, or basically copy over. As always, content over length. I just care about, do you meet the associated outcomes? But I don't anticipate that this is anywhere near as hard as either part of part 1. Yes, David. You're very red. You thought of something very funny or very embarrassing. Question?
I'm trying to be more positive, so I'm not gonna complain.
Okay.
It's not like 500 megabyte memory.
No, there's no constraints of any kind on any of these implementations. It's just getting experience thinking of things in terms of constraints and constraint solving.
So my question is like more about the class in general.
Yeah.
Is the idea of what you're trying to do here teach us stuff that will be useful for writing code at a cybersecurity firm? Like is that the angle you're taking? Cause like, besides like look up ways that I can apply this to cybersecurity, this doesn't feel relevant to what I want to do at all. Like, very frankly, I just am curious what angle this is meant to help. Cause like, yeah, I'm gonna think about 3 applications that can be modeled through constraints, right? But
Optimization, I think being able to research and determine what the current state of the art is, especially for, and even, is there a new state of the art that we need in order to update an existing process? It doesn't even necessarily have to be code, but some kind of process, some way that this company handles this particular threat or threat type. We need people who can determine with technical knowledge how to update that workflow, update that process to incorporate that so that you're always ahead of the threats that are out there. That's my thought in terms of this. So it's part research, part analysis, part application of when would this apply, identify places that this would apply in something that is interesting or relevant to what you want to do with cyber. If you want to discuss aspects of, I don't feel like that will be useful to me, That is feedback that I would love to have, just because I designed this, again, off the top of my head, just kind of getting inspired by looking around and thinking of what would be useful to people. If you feel like that's not the case, we should have a conversation, and I want to understand what would be something along this lines that does this. If you were in charge of creating a project like this that utilizes this material, how could you make it more relevant? What would you do in my shoes? Yeah, I'd be interested to hear that, because
That's a big question. I'll think on
it.
it for sure.
Yeah,
Just once I started laughing, I thought of something a little bit funny and trying not to laugh. It's funny to me in itself.
I'm just giving you a hard time. Don't worry about it. I see that like, oh, David thought.
No,
it
I
was
think
funny.
it's just like genuinely a little bit rude to laugh like that.
Terrible
It's
part,
fine.
Chris.
I'm not the most professional person myself.
I think we're just an hour and a half in, I'm just delirious, so.
Yeah, that's fair. That's fair. So I'll write up something that's more official than this, or a little bit more verbose than this, and post it at some point, probably tomorrow. But in the meantime, I would think about the exam more than getting started on this.
What does this do?
Thursday.
Yeah. Think about the exam on that. It's due Thursday.
Right before exam.
Yeah.
I am thinking probably something like the end of next week. So something. There's not that much here. Sam suggests looking into a utility like Bloodhound,
Okay.
Wait, what? What about Bloodhound?
looking into a utility like that as a way to apply this.
I would send them your way. I have to sneak one in there somewhere.
So that, I mean,
I'm confused over the comparison between Bloodhound, maybe that's to be, like, I don't know.
Bloodhound was a tool, I guess.
Yeah, some kind of active directory
Uh,
is what Sam clarifies, some kind of active directory.
oh, interesting. Okay, I didn't realize that's how it actually worked. It's just all crap, yeah.
Yeah,
I mean, I guess that makes sense, I guess to a certain degree, like if you have like a number, so if you have like 1 million users like in your Active Directory and they all have different like permissions and stuff like that, and like you can do some CSP to kind of like analyze that, see like what your structure looks like from a defensive standpoint. Just I can't imagine how you would go about doing that.
just drawing those connections. You don't have to go into a ridiculous amount of detail on it, but just thinking about, I want people to start thinking about where could these kinds of optimization techniques be used in a relevant workflow to what you do or what you want to do.
Also, if you think about
Finding
like,
numbers.
if you implement Sentry, it's actively monitoring your users, and you have like map behaviors for all your users, and then your AI are trying to.
Yeah, I mean, that's more like model agentic kind of stuff, though. I don't know, I'll have to think about it a lot more.
I do think there is something here that everyone can get something out of. I still thoroughly believe that, even after being questioned on it somewhat, but I don't know that I see everything that all of you see from that perspective. So I want to incorporate that into my process. So if you do have concerns about this, let's have a conversation. I may be able to put you on a track that you're not currently thinking about, or redesign something that is more relevant. Questions on this idea or doing something like this before I actually write it up and go do it? I'm as delirious as the rest of you, trust me. Been a long day. The fact that I'm conscious and I
guess they're next to the stop.
know. You have a future in stand-up, David, if all else fails.
keep rotating.
You always have to be analytical though, 'cause it seems like a weird joke.
Some people just play really well off of each other. My dad and I play really well off of each other, and everyone who's around us is like, why are you laughing so hard? None of what you're saying is remotely funny, but both of us are dying.
Fuck. I'm so sorry.
You go, David.
Dude,
Ooh.
Thomas took me the funny.
Yeah.
So sorry.
Okay. Alright, well, we're gonna move on and talk about backtracking search. So what happens when your constraint solver hits a dead end?
Restart it.
It's gonna be exactly the same the second time as it was the first time. It's based on strictly logic. So if your constraint solver hits a dead end, you don't have a solution and you don't have proof of a lack of solution. So there's a variable with an empty domain that would say this CSP doesn't have a solution. We've done all of the logic that we can, and we're just stuck with every variable has more than one possibility left, which means a solution may still exist. We just don't have the logical ability to find it with everything we've talked about with regards to propagating constraints. So now we actually have to go into and reuse some of our ideas for search. Because we'll start, exactly as mentioned, making selections for variable value pairs. And start searching. Given that we make this choice, is there a valid solution? If not, back all the way up and remove it from the domain. Try something else. So constraint problems really are just there to reduce the search space anyway. So sometimes it reduces the search space all the way down to here's a solution, which is awesome. Sometimes it doesn't do that and you're left with a smaller search, which is still an improvement. Oftentimes the time spent doing this is worth the reduction in domain for the search. So now imagine taking a constraint problem and applying depth limited search to it. What does that mean? How would we be able to convert the language that we've used for a constraint problem and the language we've used for some kind of global search like depth limited? How could we apply that to this? I kind of just gave it away a minute ago, but anyone want to reiterate? Or phrase it differently?
Did you give it away? I mean,
I did.
like the bullet point of the report, where?
No, it's what I said. What I said, though, it's on the slide. I get ahead of myself very frequently in this and start blabbing and then realize that when I designed this, I was setting it up as kind of a question answer, but I give the answer and just talking about a prior bullet point before I get to that point. So basically, what is a state? What are transitions between states and what are actions in this environment? Because we know that a depth limited search is between vertices and edges. So we're searching for a solution by querying what's on the frontier, visit a certain node. Now we can incorporate its neighbors. So depth limited is just saying we're going to do a breadth first search up to a particular depth and then stop. We'll start with just what's a state?
Well, in this situation, is the state is like a certain configuration of the possible domains for each node, right? Is that
Yeah,
kind of thing about
yeah,
that?
it's a partial assignment of variables.
Yes.
So we know what we know. And maybe we've been doing some guessing and checking of some other variables that we couldn't determine with full constraint solving. But a state is just exactly that, a partial assignment. Some variables have values, some don't. A transition then, or an action, is just making an additional assignment. Identifying which variable do we want to assign with which value. That'll get you to a neighboring vertex from the one that you were one move away from the existing partial solution.
I'm still a little confused on the inclusion of the word additional, like additional variable. Instead of just assigning a variable to a value? Or
Yeah, it's because it's
assigning-
one that didn't already have an assignment.
But values can have multiple variables.
In that search, let's actually draw out an example of a tree.
Yeah.
So let's say we have 3 circles and we can assign them values between 1 and 3. So a solution to this is going to be some assignment of 1, 2, and 3 to these. And maybe there could be duplicates, and maybe a constraint is we can come up with 1. But the very basic one would be that we have no assignments for anything. We kind of have question mark, question mark, question mark. There would be some children or some neighbors to this, thinking of it as a graph of all of the possibilities of assigning one of these variables some value. So we could have a neighboring one that is 1 question mark, another one that is 2 question mark, another one that is 3, another one that is 1 question mark, 1, another one that is, I can't do that, it's not a neighbor. I meant to do question mark, 1 question mark. So all of these are neighbors because one variable was assigned one value between here and there. And then from here, this would have associated neighbors, and some of them would would connect to each other as we assign an additional value. 1 question mark, 1 question mark 3, etc.
So in that case, our bottom node here, that's question mark 1 question mark would have an edge with that topmost node, correct?
Yeah,
Because
yeah, so that, yeah, you're right, but I guess this was 1 question mark, but if there was a question mark, 1 question mark, which we could get
Right at the
from
bottom there.
somewhere else. Yeah, these are still different. 1 question mark is separate from question mark.
Right, but does he not have an edge because that?
Oh,
that
yes,
top one is
yeah,
pushed
when
that
you
way?
do this, yeah, there would be a connection from here to there. These
Right,
should all technically be directed.
so they can have a lot of different directives.
Yeah, so this would create kind of a graph like that.
Yeah, okay.
But you can kind of do a depth first search within this graph up to a certain depth to try to explore this space and say, can I find a solution to this? Given that maybe the constraint solver solves some of this for us and says that if we put a 1 here, then there can't be a 3 at either of the other locations or something of the sort. So if we do that and have reduced the search space, then we can remove some of the edges from this graph that makes a depth first search more efficient. Because there's just less of a branching factor. So yeah, an action or an edge in this case, just assigning an additional variable some value. And some of those will be legal or not according to the constraints. Make sense? Good, off the top of my head, dummy idea worked out. So you can think of it as a graph, you can root it at the initial point and turn it into a tree. And that allows you to look at all possible complete assignments up to the depth that you search for that depth limited search. So in 3 moves of assignments, can we generate a solution? In 5 moves of assignments, can we generate a solution? And you would look at all possible of those in that depth first search and determine in 5 moves, does a solution exist? So branching factor at the root node is just all possible assignments for that. In the absolute worst case, that is n times d. However many nodes that you could assign times the number of possible values that it could hold. In our 3x3 example, we could pick one of the 3 to assign, and each could take the value 1, 2, or 3, so there would be 9 children to that root node. Thinking about it as a tree. At the next level, given that 1 assignment was made, you would have n minus 1 times d. and et cetera. So if we're looking at this in terms of just the leaves, where we get complete assignments, we now have n factorial times d to the n leaf nodes when we have d to the n assignments. That seems efficient.
Is it because we like can assign them in any order, like?
Yeah.
How we found that one?
Yeah,
Process around, that's why
Yeah.
it's factorial.
yeah. It's because we have n times d, and then n minus one times d, and then n minus two times d, and each one of those branch for each other one, so n times n minus one times n minus two becomes n factorial over the depth of that tree. So we do note, and we saw that some of the states are the same. The order of their assignments are different, and depending on the environment, that might matter or that might not. If we actually merge them rather than have duplicates of that, then we can reduce the space requirement. We can reduce the actual time that it takes to do this depth first search. But we've been here before, it was an alternate sequence of assignment. Then that helps save time. So reduces the leaves from n factorial d to the n down to just d to the n. Great, it's a huge speed up, but it's still exponential based on the depth of the tree. Which is why if you can get a constraint solver to get within 5 steps of a solution or some small constant, then having an exponential complexity uninformed search isn't the end of the world. Small values of exponents aren't bad. But we have to get that close to an assignment via some of the other techniques that we've talked about. So you'll often find yourselves combining these together, where arc consistency is followed by some path consistency, is followed by some kind of backtracking search, which tells you whether there's a solution to the problem or not. So here's what backtracking search looks like in terms of the Australia problem. We start with a completely uncolored graph and we root it with, all right, we've made a selection of some territory that we want to color first. Is that a valid one to start with? Do we know that this is going to have a solution? Do we need to consider starting with any other territory for this problem? We are dead. I've killed you. I feel responsible for this. Yeah.
Can you say it again, Chris? I apologize.
Yeah, so does it matter that we picked West Australia as the route for this? Or do we need to consider as additional children of this route every other possible coloring of every possible other territory?
I mean,
Yeah.
because
that won't
there's
work.
other territory would have more adjacency.
Yeah, that's what I was thinking. Like for this problem, it's inconsequential because like the idea still stands, but like if you're looking to optimize, you would pick the one that has more neighbors.
Yeah, we're actually going to talk about that next, is how do you identify which of your variables should be higher up in this tree? But we don't, in this case, need to consider assignments for everything else at the root node, because if a solution exists, then Western Australia will have a color. So there will be if a solution exists, it will exist down one of these paths. It just might be a shallower tree if we picked this territory instead of some other
So
territory.
this is an optimization at that point.
Yes.
Just get it there.
Yeah, it's a significant speed up to be able to pick the right variable to minimize how long it's going to take to find that solution, because you're immediately reducing the size of the problem by a significant.
So with this problem, sorry.
Yeah,
just a good question on that. This problem specifically, Tasmania is that little island. right?
Yeah, it's a,
So that one, like, from an optimization standpoint, would always be done last because it matters least, right?
yeah, it actually doesn't matter when it's done, but if you're trying to backtrack at some point, depth first, you don't want to go back over. It's like, all right, now that this is green, what happens if we make it red? And then go through the exact same process
Yeah.
of searching the space and in a way we know isn't going to matter.
Yeah.
Because it's independent of everything else. The color of Tasmania strictly does not matter. Another thing we're gonna talk about before we're done with this is how do we recognize those kinds of problems so that we can factor them out.
I was gonna say, wouldn't it just be better to sort of not even consider it?
Yeah.
Solving the main comment.
Absolutely. We don't want to consider it at all. So what can we do to speed this up? So performance is awful. Can we make the performance non-exponential with heuristics? So yeah, the first thing to think about is there an intelligent way to determine which variable we should assign next and not just pick them randomly? Another possible speed up, which inferences should be performed at each step? Do we want to do a pass over node consistency? Do we want to do a pass over arc consistency? Do we want to do a pass over backtracking? So when do we apply which algorithm at which steps to optimize the remaining process?
I'm sorry, can we, well, I just wanna ask a question about the previous slide really quick,
Yeah.
that number one thing. So like, in the example where it branches, it picks the neighboring one, is it possible that in doing backtracking, it just arbitrarily picks another one, like aside from a neighbor?
Depends on how you code it,
Okay,
but yeah, you could pick randomly, you could pick. A depth first search through that space will find a solution if it exists, but if you make really dumb choices, like pick ones that aren't neighbors at all,
Yeah.
then you can find that you're gonna explore that entire subtree before you realize that there's no compatibility between that whatsoever.
okay, I just wanted to check.
And then it doesn't really help you because then the very next thing you do might be to go back and say, well, instead of picking green for this, let's pick blue and try again. And there's nothing about the scope of this problem that tells the program that if we picked green and it didn't work, picking blue isn't gonna create a solution. You're just gonna go through a different ordering of these colors to come to exactly the same conclusion that that's not gonna work.
Okay. Thank you.
Yeah, great point. So second question we can ask. Third question, can we backtrack more than one step? If we can infer somehow that the backtrack isn't going to create an additional solution by trying another color or by trying another value for that. Like for instance, Tasmania was one example of that. If we try that in the middle somehow, and we realize that it's just an independent problem from the rest of the graph, there's no reason to color Tasmania different and then try every possible solution again. And then also, can we save and reuse search results?
Sorry for that question. Or that
Yeah.
Would an answer to that question for free, wouldn't it just be like, you should just create a queue of all like the best possible solutions, sorry, first one, and then backtracking. When that solution doesn't fulfill the constraint, we backtrack and pop off the first one, bring it second.
Yeah, that would work for some subset, I believe, of problems. I have a general process that will work. We're gonna go through each one of these and talk about the processes that will work for each of them, but. So first one is variable and value ordering. So you use what we call the minimum remaining values heuristic for that to try to order them in an intelligent way. Select the variable that has the fewest remaining choices in its domain. So initially in Australia, every territory can have all three colors. That doesn't really help us initially, but eventually it might be that we've identified that one value has a single, one territory has a single value, a color it has to be. If we don't consider that right away, we might do a bunch of work just to come up to the same conclusion that it can't be that color, whereas we find that faster if we actually did that in the first place. So what this does is it just, if we're going to fail, it prioritizes failing fast or failing soon, which is always a good thing. If there is no solution, we want to discover that as quickly as possible. If we've made some assignments and those assignments lead to a contradiction, we want to find that contradiction sooner rather than later. So minimum remaining values is the best thing you can do to fail early if possible. By itself performs fast things randomly or statically and frequently significantly. However, it's also very highly problem dependent, meaning that how much faster it's going to be, or even if you save much work at all, is going to be based on the domain. So thinking about, is this actually going to help us? Yes or no is a valid question to ask before you go implement a heuristic that might not do too much. There's also the degree heuristic. So if we make an associated assignment, by doing this, we're going to reduce the branching factor of future choices. We select the variable that's involved in the highest number of constraints of other unidentified unassigned variables. So if there's, this is where we select we go back to the map. If we select this territory and start there, there are the most constraints associated with it as the most neighbors. So if we start there, then since this constraint propagates to the most neighboring territories, then that is a good place to start. So both of those are potential heuristics that might have you order your variables in a way that are going to cause fast failure, are going to reduce the search space, the size of the domain, the depth of an answer. You want to push as much of that as far forward as you possibly can. So we see that in South Australia has degree 5, everything else has either degree 2 or degree 3. How many neighbors it has, it's really just all that's saying, which means that it's involved in more constraints. If something is involved in more constraints and you solidify its value, the depth of that tree is going to be shallower than choosing something else. You need fewer assignments to find the contradictions. So in the Australia example, if you select it via the degree heuristic, no matter what you do, we solve the problem in one go. We pick South Australia as blue, then we just go green, red, green, red, green, red, green, red around the other neighboring areas and done. And you would see that propagation immediately. So in general, minimum remaining values performs better than degree heuristic, but if you have a tie, so both the minimum remaining values, there are 2 variables that have 2 possible remaining. Picking which one would be better to break that tie with the degree heuristic. That's generally best practice. Does that make sense? The visualization of what these ideas are doing, are we on the same page there? See some nods and some staring off into the abysses. Anything I can say again? Anything I can try to phrase differently? How are we doing with this? We doing okay? We doing?
Been 2 hours, it's wrong.
I know, right? Me too. Just ready to go home. Yeah. Another possibility, least constraining value heuristic. Given that we're going to select a variable, we're going to select the one that rules out the fewest neighboring variable choices. This just means that we're trying not to constrain the space as much. We're going to leave open as many possibilities for other things as much as possible. So make the choice that doesn't force the associated constraints, because those are likely to end up as empty and dead ends if you make a choice that eliminates a bunch of values from neighboring nodes. It may get you closer to a solution, but it may just be useless because the problem becomes unsolvable. But so this just says later selections now have the most choice with regards to what assignments we make. So variable ordering is fail first, value ordering is fail last. Any hints as to what's going on there? Hard question after 2 hours in a classroom. Yeah, let's just go into the explanation. I think that makes sense. So in order for a solution to exist, every variable must have an assignment. So if we fail quickly, there are fewer possible assignments to backtrack over. Makes sense? Efficient pruning, we can very quickly narrow down and prune entire subtrees because we failed quickly. On the other hand, we only need to find one solution. We don't need to find every solution. So we want to look in the highest probability locations where a solution is likely to exist. So value ordering is going to preserve that. There is the largest space left for there to be a solution, because we only need to find the first one. Once we find the first solution, it doesn't matter if there are 100 more. We're done. So value ordering is totally irrelevant if we have to enumerate all solutions. The only reason we care is if we're trying to find a solution as fast as we can. But I find that that's true more frequently than not.
Trying to really get this thought out, Chris.
Yeah. Yeah.
The least constraining one, the bullet point under that leaves maximum flexibility for later value selections. That kind of sounds like I'm leaving more options open by cutting out nothing, like it just sounds like it doesn't.
So it's about the search space for the solution. If we constrain this variable significantly, then the search space is kind of small of what's left. Whereas if we constrain it less, then there are more, you're putting off the difficult decision until you're waiting till the very end to make that decision, maximizing your chances of having a solution. It's something like, I have you starting an assignment before I've given you all the information. You can either spin your wheels and try to discover a solution from a very large search space of information. But after I give you that information, how much information is going to take for you to find that solution?
Because how effective is that heuristic?
At this concept,
Yeah.
quite.
Like, say for example, Australian problem.
Yeah, so
That because the our constraint is like most neighbors.
yeah, if the constraint is most neighbors, then you want to, so it's the difference between variable ordering and value ordering. If you're doing variable ordering, then we want to figure out, we want to look at what's going to fail first fastest. But in terms of value ordering, so this is a value heuristic. We're going to look at, if I assign this particular value something, then we want to leave open the options for the neighboring. Like if I make, yeah, let's go back to the Australia map.
I didn't realize it said value. with
Yeah.
Bullet point, I was still reading variable.
Yeah, so if somehow we're in here and the options are to make this, there's no easy way to do that because there's not a pairing that's going to make an actual difference here.
The Sudoku example, I feel like
Something like this makes a constraint on both of these to be green, which is small, saying that this is not a good idea because we want to maximize the flexibility of what its neighbors can be. Whereas if we make a decision here to be red, then this can still be blue or green, and this has to be green, which is more likely to lead to a solution. You're putting off the important decision of constraining the values for these until later. More options is always better when hunting for a solution.
So we like in Sudoku, if you have like a box where like you can eliminate a single number from the domain of that box, you wouldn't want to make that decision immediately because there's too many options. So you would explore other values and other variables and then come back to that box later when the domain is smaller for it.
Yeah, so I think this is a better way to see it. The variable question is just which territory are we selecting when? And we want to select something that is likely to fail first, fail quickly if it's going to fail. We want to be able to discover that, which is why picking South Australia is a really good choice. Because if a solution exists, we know that the variable has to be assigned. And if we pick something, some combination that's wrong, we'll quickly figure that out and be able to backtrack quickly. On the other hand, which color is just saying, I don't want to pick a color that pigeonholes me into this has to be this one color, otherwise it won't work. Otherwise, if there's some other move that I can say that this can be two colors, now I'm putting off the decision where I can now look at, does one of those colors work versus not, instead of pigeonholing myself into, it's a smaller search space, there's less likely to be a solution. If that makes sense.
It just sounds like the least constraining would be slower,
Yeah,
just because it would explore other options before that aren't limited by the constraints, so.
if, here's another way to put it. I'm gonna ask you all individually a question in a room. And in order for you all to pass, I just need one person to answer it correctly. And maybe it's something like 20 questions. Maybe it's, where do you want the smartest person going? And the person who's going to give you the most information. Do you want them to go first or last? If you can narrow the search space down more and more and more, then where the most important decision happens is right there at the end. You don't want someone to go repeat a question right at the end because it's unnecessary. You want to reduce the search space or leave the search spaces open to be narrowed later. It's not a good example. There's a better example somewhere in my head.
Going back to the Sudoku example, like if I
Yeah.
could eliminate one from like, so say like my top right box has like one over here, so I know it can't be one, but there's nothing else that associates with it. There's nothing else in that box. I wouldn't want to put a 9 in there, right?
Yeah.
Because, like, is that a good
Yeah,
example?
okay.
Because so then I can go through the whole Sudoku example, but if that 9 is in the wrong position at the very end, like that would suck.
You have a very far backtrack to go.
Yeah,
So that's the variable. Which one are we looking, which cell are we looking at?
So what would
The value would be which number do we guess? Given that we've
Yeah.
selected the associated variable that is going to minimize that, what value do we want to put there? If there's now only one path for a Sudoku because it places constraints, this now has to be an 8, this has to be a 7, this has to be something else. Is it likely that all of those constraints lead to a particular solution? Not necessarily. You want to leave the optionality open to say, now we can, if we make the choice that opens up the rest of the problem the most, now we can explore that whole space in this subtree. If that makes sense. And I apologize to Sam for making her head hurt more. Pretty sure all of our heads hurt more.
I think the Sudoku example is better than the Australia one.
Yeah, yeah, I think I agree with that as well. So yeah, that's the distinction. Far into this. We're getting fairly close to the end of this, which is nice. Just a few more minutes for today, at least. So our arc consistency algorithm, AC3, is great because it reduces the domain before we even begin searching, which is oftentimes necessary. You don't just want to start a big depth first search on a near empty Sudoku. You want to figure out everything that you can logically deduce easily and then search space. You can use inference during a search. You can do something like what we call forward checking. So whenever we do an associated variable assignment, rather than just continuing and searching through that space, then do arc consistency. Make an assignment, check arc consistency. Make an assignment, check arc consistency. So for everything that's connected to the variable that you assign, you're going to check that, reduce the domain of that by any value inconsistent with what you select. In Sudoku, it's like, if I put a 9 here, then we can't put a 9 here. And if I'm guessing at that 9 and not knowing for sure, then you start removing from the associated domain so that you don't try to do something that's inconsistent with those constraints in your search. This makes sense algorithmically because a human can easily just see, all right, well, a 9's not in anything in that row, but you want to make sure of that algorithmically when you make that guess. If I do that, then reduce the domains of everything that is constrained by it based on the value that I selected. So here is what forward checking would look like applied to Australia. The initial domain is that we don't have any idea. Anything can be any color. After we make an associated selection, so Western Australia is red, then we look at the entire arc consistency. We run arc consistency. Given that Western Australia is red, we remove from the domain that Northern Territory can be red because it's adjacent, that South Australia can be red because it's adjacent. Then we make another selection intelligently and using something. We say, all right, Queensland is green. Then we run our consistency again and say, if Western Australia is red and Queensland is green, what are the associated constraints? And then you can continue to make guesses at that point. But if you run our consistency, you're capable of reducing that search space further so that you don't run into quite as many dead ends. So if we just use minimum remaining values combined with forward checking, it's especially powerful. Of course, forward checking only looks ahead one assignment. So it gives you some value, but not a tremendous amount of value. Given that we're looking at each step, what inference should actually be run? If you run maintaining arc consistency, it will detect some of those inconsistencies. So if we have a variable that's assigned a value, we then call arc consistency rather than passing in every single arc in the entire graph, pass just arcs that are unassigned that are neighbors of that. So instead of considering every possible arc, just the neighbors of the cell that was assigned. If we return failure, then we backtrack immediately. There's no reason to continue exploring that space. And this is better than forward checking. Recursively propagates back constraints when we make changes to domains. Makes sense. Some other ways to backtrack. We can use chronological backtracking. So we have some kind of failed search and we see that given the assumptions that we have made, there's a dead end. We want to back up to the last variable assignment and try a different value. If we do that, it doesn't work great. This is the kind of the Tasmania example where we know that we don't necessarily know that making a different change at a different variable assignment at that level is going to affect anything. So how do we collect that data? We may backtrack to a node that creates the same issue no matter what you select for it. How can we gather that data? It may be deep into a branch, which means that you're going to just be doing a lot of unnecessary search that you could have caught beforehand. So which assignment in a current branch might fix that problem? If we keep track of what we call a conflict set, that can help with that. So if we know that if we choose green for this, then we can't choose green for that. If we choose green for this and blue for that, then there's no way we can choose. So we keep track of a set of conflicts that we have found throughout our search so far. You don't start with knowledge of any of those conflicts, but as you start to see them, you start to record them, and then you can look them up in this conflict table rather than going deep into an assignment. Because you see that, well, I've assigned this to be this and this to be that, and I have found historically that that pair cannot lead to a solution. Done, backtrack. We can have a back jumping method, backtracking to the most recent assignment of an element of an associated conflict set. So we can get past that. Once we identify a conflict set, we jump past associated conflict sets, and instead of having to check entire other subtrees, we just go back to the next place where we could make an assignment where a solution could exist. Ooh, miserable. We better end class. This looks like I'm torturing you. It's not just you.
So in like the Sudoku example, there's. At some point, there's two boxes where. When you pick one value, like, let's say there's only two boxes left in a row, you pick one
Yeah.
value for one. And it forces the other one to be another one, would that kind of be like a conflict set? Cause then if that branch failed, we might be able to jump all the way back.
Yeah,
We made this-
exactly.
We made this decision and it converged to a failure, now we can just swap those.
We can make sure that this is not the case now, because basically, this can't be a 9 and this a 7, because somewhere down there, we found that this 9 and this 7 lead to some conflict that showed itself later. We know that these can't both be these associated values, maybe one, maybe the other. But if at any point past that, we ever make an assignment 9 and 7 again, they're in conflict. We proved that in some subtree down here. When we generate that after recursively going back up the depth first search and explore that again, we don't want to make that same assignment exploring that same subtree again when we know that these variables are in conflict.
It sounds like that would also have like, it would just spin off. If you would keep on checking every conflict from there and then.
Yeah, you have to make sure that the time spent analyzing the conflict isn't more than saved from exploring that space, so it works better on larger problems than smaller problems. But, yeah, that is a good point. I think I tortured you all enough. I do mean it, Sam. I am sorry for the headache. I'm sorry for everyone's headache at the end of today. Today was probably the densest material we covered yet in this class. I will try to make future lectures less strictly nonstop, very dense stuff. But there's quite a lot to cover.
You covered so far in the book then? Or straight
Yes.
to the book?
Yeah, everything is within chapters of the book.
Are you around tomorrow?
Yes.
What time are you leaving?
I have class until 10. I have office hours from 10 to 11. I'm meeting master students from 11 to 12 and 12 to 1. But sometime in there and or possibly sometime after that, but yeah, I would say swing by during office hours, 10 to 11, and or after. I anticipate not having busy office hours tomorrow because I'm giving an exam in compilers, and people usually come ask questions after an exam. So should be free that hour, should be free afternoon for the most part.
So I don't know, one more day of the case.
Yes.
Yeah, I'll probably find it Monday then. I teach at those times.